Let's take a look at another TrigApps topic, which is still dealing with polar coordinates, but focusing on equation conversion. Now in front of you, you see three circles, good enough to be called circles, and a straight line that's green. Now all of these curves or equations have something in common, and it's this. They can be sketched or graphed using polar equations. Now this one in purple, this is dependent on basically a cosine curve, so something like a cosine theta. The blue one would be a negative a cosine theta, and then the one in red is focused on a sine function, so there's a sine theta inside the equation. Now it's a little bit weird that you could get an actual straight line from a polar equation, because polar is dealing with a spherical shape or a circular shape, but we're going to come up with, or we're going to come in contact with an equation that actually does just that. So I'm just going to jump right in and take a look at an example of converting from polar form to rectangular form, and here's the actual function that we're working with. So if you have your calculator handy, what you could do is you could go into the mode, and so turn it on, press mode, and change the function mode, or whatever mode it's in, to polar, and then make sure it's also in radian mode. That's the best way to sketch it. So polar mode and radian mode, and press y equals, and you could punch this function right in. So I have three examples for you, and you don't have to erase any of them. You could just do R1, R2, R3, and you could sketch them as you go. Okay, now to actually convert this into rectangular form, I'm going to show you some of the steps here, and the first step is to multiply by r. And so we'll be doing that on both sides, so you get r squared equals 4r cosine theta. And I think you see why, because on the right side, we didn't have an r cosine theta before, and the only way we can convert is if we have something like r cosine theta. So then we'll use two of the equations that we've worked on, that we've familiarized ourselves with, and convert some of the things that we see here. So on the left side, r squared becomes x squared plus y squared, and on the right side, r cosine theta becomes x, and we still have that 4 hanging out. Now the next thing sort of takes us back to some of our work in prior units, and especially dealing with circles. When you look at this, you should ultimately see it's going to become some sort of circle thing, but we have this 4x that we have to deal with. So I'll rearrange. And so just subtracting 4x to both sides there, and I'm putting the x's with the x's because that old school process is called completing the square. So that comes back and we get to use the shortcut this time. So we're not going to take the long way, just the shortcut. So what we'll do, that shortcut, is this -4 right here, that's considered like our b value, so something like a squared plus 4b plus c, or a squared plus bx, one more time, ax squared plus bx plus c, and now there's no c, that's what we're actually looking for. So that's a quadratic form, and so the way we could factor that is thinking about what term is actually missing there. So the term that's actually missing there is found just by dividing by 2 and squaring that number. So -4 divided by 2 is -2 squared is equal to 4. Now this is unique because it's 4, and 2 plus 2 is 4, 2 times 2 is 4, 2 squared is 4. But if it was let's say it was a 6. If this was a 6, half of 6 is 3, squared is 9. So you can see how different those terms could become. Alright, so what we have to complete the square, we have x squared minus 4x plus 4 plus y squared equals 0. And then our final step is to just write that as a circle equation, which is factoring that trinomial into two binomials, which happen to be the same, and we have the formula for a circle centered at 2, 0. I apologize, I forgot one thing. It's kind of tricky. Because we have that 4 right there, we actually have to add 4 to the other side to balance the equation. If you caught that, way to go. But We have to actually add that because you can't just add a 4 to an equation on one side. That's illegal. So we add that 4 to the other side. And what I realized is when I noticed that the circle was centered 2, 0, the radius is actually 2. So at the very bottom, that's our rectangular equation. Now just notice real quickly, you can't punch that into your calculator as is. It has to be in a y equals form. So that's one of the special things about polar form is you could sketch circles and ellipses without having to create two separate equations or two functions. Let's check out one more. This is a little bit trickier to start with, but it's actually a lot shorter in the process. So notice that r equals -2 cosecant theta. Cosecant theta is 1 over sine theta. But you know, what should we do here? It's not very clear. If I were to change this cosecant theta using the identity 1 over sine theta, notice that we'll have -2 over sine theta. That doesn't really seem that helpful. But if I divide by cosecant theta, I have r over cosecant theta equals -2. It's starting to seem like maybe I could do something unique here. That cosecant theta, 1 over that, is sine theta. So I could simply bring that cosecant theta up as a sine theta. We could write it a different way, but it's really not necessary. I'd like you to be familiar with this. Now on the left side of the equation, that simply becomes y. So y equals -2. Oh, that's kind of unique. That's the equation of a line, and it's a horizontal line at y equals -2. So that was a quick one, but it required just a little bit of thought at first. So if you see cosecant or secant, then you might think that it's going to be a horizontal line or a vertical line. And just to show you, there's that picture of that horizontal line right there. So pretending that's -2 there. Okay, so those are two unique things. The first one, we're multiplying by r. You can't just square r. Notice, if you square both sides, that gets you into some dicey situations. This one, we're just getting the cosecant and r together so we can manipulate it. And finally, we have a circle. Notice the center is at 2, 3, and the radius is √13. And what we're doing here is we're converting a rectangular form to polar form. Now we know it's rectangular because there are x's and y's. So get ready for this one. There are a few steps here, 4 or 5 steps, a little bit more involved. The first thing that we'll do is expand. So x squared minus 4x plus 4, and expanding the y's. Notice how we see like little hints of this completing the square going on, but we're actually going the other way. So the next step, we'll rearrange some of these terms. So I'm putting the x squared with the y squared because that's going to become an r squared. I'm getting the 4x and the 6y together. So -4x, -6y. And finally, if I subtract 4 and subtract 9 on both sides, I will get a 0 on the right side. And then this is the point we'll actually substitute the other equations in. So let's see here, that x squared plus y squared is becoming an r squared. And then, let's see here, this -4y is becoming a -4r sine theta based on trig, or just the formulas I gave before. Okay, and that's a 4x. I think you knew that. And then -6y. Oh, so then that must be a cosine. Shoot. Cosine theta. Sorry about that. -6 sine theta. Alright, so let me double check that. We have r squared, we have 4x, which becomes 4r cosine theta, 6y, which becomes, yeah, that's correct. Almost correct. We have an r right there. Okay, beautiful. Now what you should notice is that we could factor out an r here out of all of these components here. So we have an r minus 4 cosine theta minus 6 sine theta. equals 0. So now why did I do that? I don't necessarily know. I'm looking at this and I'm trying to really solve for r, and I can't just square root both sides. I can't add or subtract some things to the other side and square root it. Or maybe if I do it, we get two different versions of this. But I figured if I factor out an r, I would have two equations. And so one of those equations here on the left is would be r equals 0. And then the other equation would be, if we add 4 cosine theta to the other side, we get 4 cosine theta, add the sine theta on the other side, 6 sine theta. And so what I would do now is I would actually take both of those equations and sketch them. And you could put one of these, I put r equals 0 inside r3 and r equals 4 cosine theta plus 6 sine theta into r4. And when you think about this r equals 0, what that is it's going to sketch 0, 0 just repeatedly, however much time you give it. So it's basically a circle with radius 0, which is simply just a point. So that actually doesn't make any sense to include that. And moreover, the reason why we don't really need to include that is because r equals 0 is included. So it's included in this equation right here. Think about this. If you plug in 0 into cosine, 0 into cosine, you get 1, so you get 4 plus 0, and so you get 0, 4. But then eventually, plugging in some points will yield this r equals 0 value, and you would see that if you'd sketch it. So in conclusion, this is the equation, this is the polar equation of this rectangular equation, and because r equals 0 is on the graph of this equation, only this equation is needed. Okay, so you are welcome to sketch a picture of this, and it's really pleasant to actually plug this into an r equation to see it sketch a circle. And you'll see the circle that's centered at 2, 3 with radius root 13. Alright, so those are 3 examples to show you conversions. The next time, super exciting topic, we get to see all the sketches, all the graphs of roses and limacons and infinity signs on a graph. Thanks a bunch for watching.